Hello, so in this video, I want to talk about Pythagorean triples. I'm pretty excited about this topic. I think a lot of people have checked if three numbers would form a right triangle using Pythagorean theorem before, but going the other direction, trying to look for three integers that satisfies Pythagorean triple, that's not an easier direction. So in this video, we'll figure all that out. Let's jump right to it. Okay. So when we say Pythagorean triple, we're talking about integer solutions to a squared plus b squared equals to c squared. So I'm sure you have seen 3 squared plus 4 squared is equal to 5 squared. Another example like this is 8 squared plus 15 squared happens to be exactly 17 squared. And I would like to present a theorem that kind of characterize all these triples, like how to characterize all of these. So here's the theorem statement. So Pythagorean triples are integer multiples of the form 2rs, r squared minus s squared, and r squared plus s squared. Or this other form, but you can kind of see that they're pretty much the same. The only difference is that the r squared minus s squared term and that 2rs term is swapped between those two. So notice how in a squared plus b squared equals to c squared, the role that a and b plays is kind of symmetric, right? So of course, if you swap it, you're gonna get another solution to it. So that's what this is saying. For any integer r and s. So you pick any two integer r and s, and then it forms this Pythagorean triple if you plug it into this formula. And conversely, if you find a Pythagorean triple, then it has to fit this form for some r and s. Or actually, you could multiply these by any constant, and you'll still get a Pythagorean triple. So it's either this form or it's a multiple of this form. So that's what we're gonna prove in this video. So one direction is much easier. So if you have something in this form, you could just plug it in and distribute and check that this satisfies a Pythagorean triple. All the terms will match up on the left and right. So if it's in this form, it's a Pythagorean triple. The harder direction is that if it's a Pythagorean triple, then it's either these guys or multiple of these guys. So let's see how this plays out. Okay. Multiplying by n in each of these three a, b, and c, well, when you square, it'll factor. It'll increase by factor of n squared on both sides of the equation. So it's still going to work. So once you find a Pythagorean triple, you can multiply by any number in each of a, b, and c, and you'll get another Pythagorean triple. So that paragraph takes care of one direction. So if it's in this form or multiple of that, it is a Pythagorean triple. So let's start with a Pythagorean triple and see if we can find R and S that fits this form and a multiple of that. Okay, so here's the genius of this problem. It first seems kind of intractable because we have to find three numbers, A, B, and C. But really, if you divide both sides of the equation by c squared, we'll transform the problem into something that's two variables, x squared plus y squared equals 1. So I'm trying to draw a picture of what's happening here. So if we have this Pythagorean triple ABC, so it's a right triangle. If you divide everything by C, you'll rescale this to a point on the unit circle. So there's benefit and drawback to looking at it this way. So one big benefit is that you reduce one number or variable by one. So A, B, and C was three different numbers we have to deal with. X squared plus y squared equals to 1 is only two variables. So now it's easier to get a handle on what the solution looks like. But remember, we are losing some information here. Because we've divided everything by C, we have to, once we understand the solution of X and Y, we'll have to translate back to ABC by multiplying everything back by C. So we'll have to do that later. But for now, that's a step forward. We have a simpler form of the equation. And A, B, and C, we want it to be integer. So, but if we divide by integer C, now it's a rational number, X and Y. So that's also changed. And then now we use the parameterization theorem that we proved last week. So if you have a rational point on a unit circle, you could describe it in this form for some rational t. So now we've gone from three variables to just a single variable t. So this is quite a bit of progress here. Or it could be -1, 0. Okay, so okay, let's say we have a Pythagorean triple and we converted it to this form, and we have because we know it's a rational point, we have this rational number t. So let's write down t in ratio of integers, s and r. And let's choose s and r so that they're in its lowest term. So what I mean by that is that their greatest common denominator is 1. They are relatively prime. Okay, so if you plug in t equals s over r into this form, here's what we get. Okay, so this is the expression we get. And there's a fraction inside a fraction. This is really messy. So one thing you could do is multiply top and bottom each of the x and y by r squared. If you do that and then simplify, here's what we get. All right. So remember, rns is integer, and this is the point xy on the unit circle. Now that we understand what x and y has to look like, so we know x and y has to look like something like this. We want to convert that back to in the form ABC. So remember, we had to divide by A and B by C to get the x and y. So to get back the A and B, you have to multiply by C. So let's say we multiply each of the terms by C. So we're multiplying C to this term and that term. So here's how I want to rewrite it. So let's see. We have r squared minus s squared divided by r squared plus s squared. Let's pull the r squared plus s squared in the denominator out. So here's what we have in front. When I write this expression multiplied by the triples, what I mean is I'm multiplying this to each of the three coordinates. But they're common factors, so I'm putting it in front so I don't have to write it 3 different times. Okay, the same with the y term. So c times this. I'm going to pull out the denominator of r squared plus s squared. So I have that in front. And the c on the third coordinate, that's just c, but I'm going to write down c by multiplying top and bottom by r squared plus s squared. So I could pull out the c and over r squared plus s squared out into the front. And here's what we have left on the third coordinate. Okay, so this is an important form that I wanted to write down. So I'm going to call this equation star. Let me give myself more room by erasing that. Okay, so notice this is a lot closer to the form that we were trying to get to in the statement of the theorem. We have r squared minus s squared, 2rs, and r squared plus s squared. So the theorem is claiming that it's either this form or it's integer times some constant multiple of this form. So the best case scenario is what we pulled out into the front. This is some integer, but it turns out that it doesn't have to be an integer. So let's call this guy z and see what it would have to be. If it was an integer, then we are actually done. It's a constant multiple, integer multiple of the form that we set out to prove. It turns out that even if it's not an integer, it's very close to an integer. What I mean by that is it's a half integer. So half integer is integer divided by 2. So maybe it's something like 3.5 or 6.5, or it's something 0.5, right? It's 1/2 more than an integer. So how do we see that? Well, let's look at it. So let's see, we know that z is a rational number. So let's say this z is m over n, where m and n is in lowest terms, so they're relatively prime. We have to multiply this guy, z, to this a and c here, which is an integer. So that means that n has to divide r squared minus s squared, and he has to also divide r squared plus s squared. If they don't divide by it, you still have a fraction when you multiply back in, and you don't have an integer solution a, b, c. So the only way this denominator is going to cancel is if this divides what we're going to multiply to. I hope that made sense. So, okay, n divides this guy and this guy, which means it's going to divide the sum of those two terms and difference of those two terms as well. So if you add up these two terms, r squared minus s squared and r squared plus s squared, then s squared is going to cancel out and you get 2r squared. If you look at the difference, then the r squared will cancel out and you'll get 2s squared. But note that r and s, they are relatively prime, right? Because if r and s is relatively prime, then r squared and s squared has to be relatively prime because of their prime factorization. If you square each of the multiplicities, they still don't share a prime factorization, so they have to be still relatively prime. So if you can divide both this and that, then and r and s, they're relatively prime, that must mean that they divide too. So n, the denominator on the z, has to divide 2. So there's only two options. N could be 1 or n could be 2. So if n is equal to 1, then it is an integer, and we already talked about that case. We're done. If n is equal to 2, then it's a half an integer. So therefore, z is a half integer. Okay, so let's consider the case where z is a half integer. So remember this expression z, this is our z, times c has to be an integer. If z is a half integer, that means r squared plus s squared has to be an even number. Okay, so r squared, this has to be even. Otherwise, the divided by 2 part will not cancel out to get an integer. But look, so r and s are relatively prime, so they both have to be odd. What I mean by that, if they're both even, they're not relatively prime. If one of them is odd and the other one is even, then odd square plus even square is going to be an odd number, which we know that's not the case, right? So they have to, R and S both have to be odd. Now, if they're both odd, then when you add them together or take a difference of each other, it's going to be an even number, because odd plus odd is even, and odd minus odd is also even. So let's say we're going to define R, capital R, as the average of R and S, and capital S is the difference of R and S divided by 2. They're both integers because R and S are both odd. And we're going to make this substitution. So we're going to say, if we add it together, we'll get little r. And if we look at the difference of each other, we'll get the little s. So what we're going to do is we're going to substitute. The little r is going to be big R plus s, and little s is big R minus s. If you look at all 3 of these terms, here's what we get. So the difference of the square is going to be 4 times big R times big S. The 2rs is going to be 2 times the difference of the squares of the capital R and S. And the sum of the squares is going to be twice the sum of squares. Okay. So let's substitute, see what it looks like. Okay. Here's what we get in the end. And because each of those all have 2 in common, you could pull out the 2. And this is 2 times z. So remember, z is a half integer. So 2 times half integer is going to be now an integer. And the form looks flipped, but this is one of the forms that we desired. So it is an integer times this particular form that we said we were going to prove. So that's it. It's a long proof. This probably requires another watch, maybe, or 2, to really understand the details. But this does show that if you have a Pythagorean triple, then there is an integer and R and S that fits that form. Okay, so now that we have this, we can actually generate a whole bunch of Pythagorean triples. So what we could do is we can just pick an R and pick an S. So I just chose 2 of them. Oops. If you pick R equals 5 and R S equals to 2, all you have to do is just plug it in this form. And we get 21, 20, and 29. So that's a Pythagorean triple, which is pretty cool. Anyways, I think I'm going to end the video here. I will see you in a bit.